Anyhow, what we're going to do today is basically see what are the modes of the system for 1D lattice, 1D plus a base, meaning that we have more than one atom per unit cell. One D disorder, which I'll just describe, not with a full solution, but it has interesting implications. And 3D, hopefully we'll get to it. If not, that will be the next lecture, just so you would be aware tomorrow there's no lecture. Memorial Day there is Okay, so let's start with 1D. So in equilibrium or at low temperature we have a 1D lattice. Distance between each lattice point is A. Let's call it the X direction. Just so we'll have some coordinates, let's call this in 0, 1, and 2, and so forth. And continuing to infinity. Okay, once we're not at equilibrium, there will be an atom somewhere in the vicinity. Okay, what else can I? Pay attention, I'm treating here a 1D where the atoms are confined to the 1D. Otherwise, I could have here a 1D lattice, but the atoms moving in 3D. That's not what I'm doing. I could have an atom somewhere here. If you'll think of it, if you're taking a string, that's essentially what happens. But here, I'm confining the atoms to a 1D structure. Real 1D, as I can't move out. Okay. So, I'll describe, as we did in the previous lecture, the movement from the point of equilibrium as U A U 2A U minus A U minus 2A, and in each case it's the distance between the point of equilibrium and the point which the atom actually exists at the moment. Okay, so if I want to describe the motion of these atoms, what do I need to do? Someone has an idea? מה אני צריך לעשות בשביל למצוא את התנועה של האטומים? What should I do in order to solve the movement of these atoms? Right, at this point in your life, it should be a knee-jerk reaction, something automatic. Write down the Hamiltonian, extract equations of motions, solve them. That's the usual recipe, and exactly what we'll do here. So, the Hamiltonian okay. What else can it be? Kinetic energy plus, and here I'm doing my first step towards solution. I'm not going to solve for any kind of interaction. I will assume that it's a small deviation around the equilibrium, and therefore I'm only interested in the potential energy in the harmonic approximation, nothing more. Okay. What do I know if all the points are at equilibrium? All the atoms are sitting at equilibrium. What is the harmonic potential? Well, if I'm very pedantic, it doesn't have to be 0, but it's minimum, and since it's minimum, I don't care about it, so I can write 0 without losing any generality here. Okay, if they're not at the equilibrium points, so if none of them has any deviation, all u's are equal to 0, I get 0. So that's okay. If they have deviations, I'm caring about the relative deviation one from the other. K depends on the potential, but at the harmonic approximation, it's just the second derivative of the potential. That's all. If you want, I got to a point where I can imagine this problem as a lattice with springs between the atoms. Why it springs? Just because I chose a harmonic approximation. It's not that I believe that there are springs. Okay. So I can write down the equation of motion.
You don't need to put a specific x on k, like x of equilibrium or something, that will be constant.
I'm looking at the deviation at each point. N goes here.
K depends on x?
No.
So we need to put something in it. Some kind of x.
What do I do here? As usual in any expansion, Taylor expansion, I'm taking the value of x at the point of equilibrium, the point around which I do my approximation. usual equation of motion. If you want it in a less dramatic or sophisticated language, we're just writing F is equal ma. This is F. Okay, I'll keep my notation. Okay, I'll use here large N. My notation will be consistent.
What is phi, all of them?
Phi is what we did last lecture, which is writing down an explicit potential. We know how to write it for molecular or ionic systems. We said we don't know so much how to write it for covalent systems, but it doesn't matter. At the end of the day, whatever is the form of the potential, it ends up being a spring constant. That's why harmonic approximation is so popular in physics.
Porque U, que tenga potencial.
No,
Potencial es igual to 0.
no. U is exactly what's indicated here. The distance from the point of equilibrium for each.
Ah, okay.
Don't confuse it with large U, which is the potential. Small u here is deviation of U of 0 is the distance indicated here in red between the point of equilibrium and the point that the atom is at the moment. Okay. So if I'm looking, where do I have dependencies on U of n for any particular n?
For two of the parts we have.
I have it at two of the parts. Let's say n equals 0 here and here, because U0 appears in both of them. So I perform the derivative. So I get k derivative here, the 2 cancels. Minus. No dependencies anywhere else. Pay attention that these are n equations. For each U, I have an equation, I have n U's, because I have n atoms in my lattice. No, nowhere else does it appear. Okay, so let me write it down in a bit.
There isn't supposed to be a minus also on the outside? Because there's a minus.
Yep. Good. Okay. If I'm looking on this form, someone can tell me what it is? Yeah, exactly. It's the second derivative of space if I wasn't in a discrete system. This is a discretization of the second derivative of space. Okay, but since lattice are discrete, we have here a discrete form. Okay.
May I ask a question?
Sure.
Why did we write that the U harmonical is the difference between the UNA minus UN plus 1A? Do you refer to this as the oscillar harmonic oscillator?
Just because if the distance between them is A, the distance of the lattice, I have no interaction. Because the distance of the lattice is simply the point of minimum harmonic energy. So it's 0. Could have written here plus U of R plus this and minus U of R plus this and go through 2 steps and get exactly the same. We did it actually in the previous lecture. Okay. Another step that I need here. Boundary conditions. Can solve differential equations without boundary conditions.
You mean something that's circular, maybe?
Indeed, exactly. That would be the easiest case because at the end of the day we think of something very big and at the moment we don't want to deal with the effects of boundaries of the lattice edges, so we'll just connect it into a circle if you want, or in the more professional terminology, cyclic boundary conditions. So I want that U of so this is cyclic or periodic boundary condition. So I'll guess a solution and show that it's a solution. It won't be a surprising solution, but because all of you did waves, the course in waves. hope this form is not surprising to anyone. And basically, what would be a solution here?
You need to relate K to omega with the dispersion relation?
Exactly. Once I know the connection between omega and K, which is known as a dispersion relation, and I can fit it into something that's reasonable, I have the solution of the problem, as in any wave problem. You're asking or stretching?
Just stretching.
Okay, so another thing that I should take into account is the mere fact that I'm putting into it periodic boundary conditions already tells me something about the problem.
K is an integer.
K is not an integer, but it's discrete. It's because in order to fulfill this condition with what is written here, so what's un plus n? Okay, it's equal e to the power I k n a plus I k. Okay, I just substituted u of na to u of n, capital N times a. This guy should be equal 1, meaning this guy should be 2 pi. So it's not any k, but only small and large. This is p. Okay, just multiply it and you get okay, with p equals 0 plus minus 1 plus minus 2, so on and so forth. Yes?
What is the meaning of the big N?
I decided that I'm taking periodic boundary conditions. So after big N lattice points, I'm returning to the same point.
It's a whole lattice.
It's a whole lattice. Okay, so we have this guy, and it tells us which are the possible Ks. Okay, so let's take our solution, substitute it into the equations, and see what we get. From the left-hand side, I have a second derivative of omega. It sends me minus omega squared, and nothing else changes. Okay? And on the right hand, I have here u of n minus 1a. So instead of n, I'm writing here n minus 1. Let's use this for 2. Okay, so 2 e to the power I k n a minus I omega t minus e I k n minus 1 a minus I omega t minus e okay, just substituted our solution into the equation. Okay. And I'm left with okay, let me get rid of the minuses also. That's all that I'm left with. Some skepticals.
What about the M?
What M? Ah. True. So let's recall our 9th, 10th grade trigonometry.
2 times cosine.
Yeah. So after the whole exercise, I get a dispersion relation of leave this picture here.
Divided by
For some reason. Getting M all the time. Or I can write it down. Another trigonometric identity. Okay, so what does this mean? Okay, let's just draw a diagram. Omega is function of k. First of all, it's important to remember that my points are discrete. That discreteness comes from the boundary conditions. So in principle, if I'm talking about a very large system, n goes to infinity, and at the moment I can disregard these discrete points.
Richard,
Yeah.
I think you have no, you don't have square 2, you have 2 in the last נוסחה.
Equation.
Because of the identity, you get another square 2.
Correct. So that someone pays attention. So this is 4 and this is 2 because I didn't measure it.
The first one is okay, I think. You just
No, this is okay, this is not okay. Right. Just the identity is twice k squared. K half. Okay, good. A more important limit k is limited by pi over a. Someone can tell me, give me an intuitive reason for that?
n שווה 1 למרות המינימום, לא?
You're on your way. Excuse me? When we're talking about a discrete system, we're limited in what case are relevant. For the simple reasons that you should always remember that a Fourier transform K of Fourier transform describes behavior at 1 over K distances. Now, there's no points that are closer than A. So it's meaningless. You don't, if you want, you don't need or you can't have values of K that are smaller than A. Just because, let's assume for reason, for the sake of argument, that we have a K that's equal 2 pi over A. It will be identical at all points to K, to the value of K of pi over a. No additional information in it. Silence. To repeat it?
Yes.
Okay. Okay, what I'm doing here, I'm giving a value of a function, u, at given points, right? Okay, this is my lattice, these are the points. At each point, I'm giving the value of u. Right, so let's say I'm looking at the zero mode here. What does that mean? Let's look on the solution. If k is equal 0,
P is equal 0 as well.
so doesn't matter what is n, all of them have the same value, right? So for the 0 mode, all I'm describing is all these guys are moving with the same distance. Right? They can't have anything else because each one of them shows the same correction. Okay, so that's the 0 mode. I should have written here 0. It's also. Okay, let's dive into the physics. What is omega at the end of the day? It's connected to energy. No contribution to energy. Why?
Because
All of them moved the same way, and therefore didn't cost me any harmonic energy because all of them just the equilibrium points moved, but the distance between them didn't change. It's equivalent if you are taking a system with springs between them, just moving it here. What happened to the energy of the system? Nothing. Because all distances remain the same. And therefore the dispersion of omega equals 0 of the 0 mode is 0.
Will the particles have the same P? Like, in this case, all of the particles have the
This
same
is a P. 0, 1,
But
2.
can I have two particles that have different P's at the same
No.
system?
You can have, what is, okay, well, we'll do a quick repeat of waves. What am I doing here really? I'm expressing the system as function of modes. Like, if I'm looking at a real-time picture of the system, I see something like that. Each particle moves in some way if I'm taking a snapshot at a given time. But what is the solution telling me? That I decompose all these motions into just a summation over different modes, right? And modes have the same p's. That's what a mode means. That I have a motion that is described by the same law for all the particles that are described by this mode. So, for those of you who are somewhat musical, it doesn't include me. Basically, this tells you that you have some what's it called in music?
Harmony?
Some harmony. So if all of them are moving the same, you have a pure harmony. If you have a combination, they don't move in the same way. Okay, so the zero mode is just this mode. The first mode, what does it tell us? Okay, what is the first mode? 2 pi over NA. Okay, N is large. So the deviation of the first mode is quite small one compared to the previous one. It becomes a bit larger and at the end, the system it's just one sinus mode. So I went through the whole system and saw one sinus mode through it. Yes. That's P equal 1. So if I'm looking at each two particles in the lattice, the distance between them didn't change much, but if I'm looking on the whole system, it went through one twist. It has to return to the same value after large n because of the periodic boundary conditions. P equal 2 means that it's that it went through two ups and downs. So it means that that particles that are close to each other have a larger discrepancy, a larger movement between them. P equal n over 2 means, and here I'll draw it again. So if this guy is here, these guys are exactly at the opposite. And again, this guy returns to the original place. Okay? So basically here I have n oscillations between them. If I have stronger oscillations, it doesn't have any meaning because I don't have points. If I'm looking on this guy and putting here an even stronger oscillation, has no meaning because these guys don't correspond to any lattice points. And this comes from the simple fact that I have a distance a between lattice points and I don't have what to describe in between those a's because I don't have points there. The higher values of k, smaller or larger than pi over a, contain no additional information. if you want, and that's for those of you who had really understood the previous lectures, what is pi over a? Exactly, and if I add an additional constant of pi over a, has no meaning, right? That's exactly the inverse. That's it. We'll return to it, especially when we'll solve the Schrödinger equation of electrons in such lattices. It will be important there. Okay, so what do we see? At the beginning, small sinus, it's equivalent to k over a, so W is proportional to over m. Linear. Well, of course it's continuous, it's my drawing, but at very large k, close to pi over a, we have here sinus of pi over 2. Sinus of pi over 2 is a constant. So the upper bound here is so this is a dispersion relation. Such a behavior of omega proportional to k is known as an acoustic mode. Means that omega is proportional k for small k. Someone can give me an example of another wave phenomena that behaves this way? What behaves like omega equals ck? Light. So it behaves linearly with k. The only difference is we don't have this behavior at larger k. Someone can give me a physical reason? As far as we know, space has no discreteness, so when I come to describe the wave at every point, my distance a goes to 0, meaning I never hit this point. It goes to 0, so that's infinite k. I don't have a limit there. Or to the best of our knowledge, we have no limit there. So an acoustic wave is, in some sense, the simplest behavior that we can get out of a system as long as we don't know anything about its structure. Once we know that it's discrete, this behavior can't continue forever, which is this part of the behavior. So this form tells us that for k's that are much smaller than 1 over pi over a, I have the usual linear dispersion. Omega is some constant times k. For larger k's, which are already of the order of pi over a, where I see the effect of the discreteness of the lattice, it goes to a constant. Yeah.
On the other side is like a mirror.
Exactly, that's why I wrote. And over here, same thing, same limit. Again, I can't go beyond minus pi over a. Okay, that was part 1. Okay, let's assume now that we have an additional atom in our 1D system. Again, if I'm not at equilibrium, we'll have to talk about u of d, u of a plus d, u of 2a plus d, and so on and so forth. Okay. So, as we have seen, what is important for me is the harmonic part. And for simplicity, instead of using u of d and so forth, I'll replace them by u1 and u2. Okay, so I don't have to write each time plus d plus 2d plus d in every spot. Okay. Just again, when I'm going through U1, U2, U1, n plus 1, so on and so forth. Why do I have K and G? The two atoms could be at different distances with different potentials between them. So the derivative doesn't have to be the same, so I'm using two constants here, K and G. Everything else is the same as previously. Equations of motion. For simplicity, I'm using the same m, but you can go through the calculation also if they have different masses. We have now one primitive, always you have one primitive cell, but this primitive cell has two atoms in it, at positions Na and Na plus D. Completely the same treatment. The only thing that I take into account is now any guy in the primary position U1 has two neighbors U2 at n minus 1 and U2 at n, and vice versa. For any U2 you have U1 at n and U1 at n plus 1. What are the solutions? Won't come as a great surprise. That I have two solutions with two amplitudes. But the same idea. Now we have to substitute it into our equations and see that it actually solves the equations. Everything else remains the same. The only thing is that the amplitudes at the 2 points don't have to be equal. Okay, let's see if this actually solves the problem. So substituting will end up with the following. Okay, what did I get here? Just as I say, substituting. Look, derivative according to u1 or u2, both of them will give omega squared, n times omega squared. The only difference that in the top equation it will be multiplied by epsilon 1. In the lower one it would be multiplied by epsilon 2. Okay, what else do I have? If it's the same NA, I'll just get K times epsilon 1 or K times epsilon 2. The only case where I get something different is in the case here n minus 1 and here n plus 1. Therefore I get e to the power I ka, and here e to the power minus I ka. All others just disappear out of the equation. Okay, let's see if someone here remembers anything about linear algebra. What is the condition that these two equations will have a solution?
The determinant is
Very good. I'll just write down the determinant and see if I can get 0 out of it. Okay? This term, this times this is equal to the absolute value square. The absolute value square is the real times the complex, sorry, the term times the complex conjugate, which is exactly what's written here.
אמור להיות סוגריים אולי, בהשוואה ללמוד עצמו, סתם שיש סימטריה. אמור להיות סוגריים, בהשוואה ללמוד עצמו לפני ה...
Yes, of course. Okay, so I'm using this in order to get the dispersion relation.
יכולים לעבור שנייה שתי שורות האחרונות
Just a moment.
על המעבר למטה.
Just a moment. In order for me to have a solution to this type of equation, the determinant should be equal 0. Okay? This times this is just written here. This times this. Pay attention that this is the complex conjugate of this. It's in the parentheses. So I'm writing it like this. Epsilon 1 times epsilon 2 drops out because both of them have epsilon 1 times epsilon 2 for them.
Thank you.
That's all. As usual, dispersion relation tells you for what value of the connection between omega and k in order that the solutions that I guessed can be fulfilled. That's the condition. At the end of the day, it's a bit cumbersome, but at the end of the day, all it tells you what will be the connection between omega and k. That's all I want to add. So I just wrote explicitly the right hand. And
מה שכתבת למעלה זה רק ה-K פלוס שיבה, נכון? שורה ראשונה?
this is this.
כן, אבל...
And this just I took it here and performed the multiplication. And more, nothing less. Okay, and get also E over E2 equal K plus G K A and okay, so we did a complicated calculation, we got a result, and this point is perhaps more important for you than the whole calculations that we performed. How do I know that this mess is a correct solution? Someone has an idea how I will check it?
Substitute G equals 0 and see if it's the same as before.
If I'll take G equals 0, I won't have any more a lattice, because it means that each two particles don't speak with each other. So taking G equal 0 is not a good way to check it. What do I need in order to compare it with the results that I know?
G equals K.
G equal K. You understand that if K equals 0 means that you have G equals 0. You have interaction between each pair, but no interaction between the pairs. So that's not a lattice, that's just a bunch of molecules. Okay, so let's see what we get here if we just substitute. So I'm checking. Okay. Missing here a K squared.
K go G now, it's
No, just okay. Yeah.
ה-K וה-G בשורה השנייה בלמעלה, את עצמו לא צריך להיות בריבוע.
This guy. Just unit-wise, no. But, okay, this shouldn't be squared. Here, simply from units, I know that previously omega squared is proportional to K over G, and K over N, not K squared over N. So, mistake was just writing here square. Okay. That's not very similar to what I have gotten, but let's see. The minus part. Let me rewrite. I'll write it here. Okay. And if I'm using this and replacing this one by was 2 sinus half k over a. Word. So for the plus result, I get, excuse me, for the minus result, I get the previous result. For the plus result, I get something new. What happened here? Let's look a bit more carefully at our solution. Anytime I have a result that I'm having problems in trying to understand what it really tells me, the best thing to do is to go to some limit that I think that I understand. What is that limit? Small k. Small k, I had previously a simple linear dependence. So let's just write here down the solution for a small value of k. Okay, I'll just replace cosine its expansion close to k goes to 0. Yes. Okay, let's pull out k plus g square outside. So I have here k plus g squared. Okay, I'll write it down explicitly. Over n plus minus 1 over n k plus g squared. This term, and this term. This is not here. Okay. Pull out k plus g squared outside. Okay, remember that we're doing it for small k. Okay, so we have two solutions. And for the minus, so I subtract this, just a moment, I subtract this from this. So I have to take the small k into account because otherwise I have nothing. And it will give me this solution we understand. Take a square root and omega is linear with k. some dependence on K and G. If we put in K equal G, we'll get exactly the results that we got before. This result, and therefore this is the acoustical mode. Result is strange. First of all, what does it tell me? Right, omega does not depend on k, which seems very strange. At least for small k's, it's some constant. How can we understand it? Okay. If I go back and look on the relations between E1 and E2, I'll get here the acoustical mode corresponds to the similar behavior of the two atoms that take part in our wave. Meaning the first atom moves in a similar way to the second atom. What it actually tells us that both this. So if I'm indicating here the positions of the first and the second atom in my lattice, so if these are the points, if the first atom moves, the second one moves in the same manner. So basically it's very similar to the previous case. We have here a wave where the two atoms, both of them are pushed in the same direction. Epsilon 1 is equal to epsilon 2. We have a regular acoustic wave. What is this mode? This mode basically tells me that if I'm looking on the lattice,
The black one's moving one direction and the green one moving the other direction?
exactly.
Do we need to assume anything about the distance between them?
No.
Because they need...
Well, both of them should, the movement should be smaller
Than the distance.
than the distance between them. So let me add also arrows to make it even clearer. And here it's, if this one is in this direction, so what happened here? basically the two atoms in the unit cell are moving in opposite direction. So basically, they don't care about the lattice of an all as a whole unit. They're just moving one compared to the other. Meaning that we have something that doesn't depend on K, which tells us something about the motion of the whole lattice. Here, each individual cell has an additional mode. And this mode is known as an optical mode. Okay, now you can come and ask me, lovely, but what happened to your argument if G equal K? I should see the same behavior as previously. I'll talk about it in the beginning of the next lecture, but I throw it as a challenge to you. Perhaps someone can talk about it in the beginning of next lecture, come up with an explanation what happened here. Because at the end of the day, when I take G equal K, I should see the same behavior as previously. The fact that I, in my imagination, push two atoms into the same, into one primitive cell shouldn't change the physics of the system, since I'm deciding about who to call whom, not the system. And my way of naming things shouldn't change the behavior of the system. Okay, so see you next week. Think about the solution, and I'll be happy to let someone explain.
רגע, אז מחר אין הרצאה?
יום הזיכרון, יש טקס בכל הלימודים באוניברסיטה בין 12 ל-2 מבוקרים.